The greatest new resource race is not happening on Earth. It is unfolding inside the darkest places on the Moon. For generations, the Moon seemed finished. A silent sphere of gray dust. The Apollo missions returned rocks from its sunlit plains, and they appeared almost completely dry. That picture became our reality. The Moon was a destination for exploration, not a place anyone expected to need. Attention eventually shifted toward a landscape almost nobody had ever seen directly. Near the lunar South Pole lie enormous craters whose floors have remained in complete darkness for billions of years. Because the Moon tilts only slightly, sunlight never reaches their deepest interiors. From orbit, those shadows looked empty. Yet governments and space agencies began concentrating their plans around them instead of the familiar equatorial regions. The object itself had not changed. Our understanding of it had. Something valuable had to be hiding where sunlight never arrived. The answer did not come from a person standing inside one of those craters. It came from a deliberate collision. In 2009, NASA sent an empty rocket stage crashing into the floor of Shackleton Crater. The impact happened in darkness, invisible to ordinary cameras. Instead of watching for a dramatic explosion, instruments measured the cloud of material thrown upward into sunlight. Spectrometers searched that expanding plume for chemical fingerprints. They found them. Water vapor appeared among the debris. Tiny ice particles had been buried inside the frozen soil. Earlier orbital observations had already hinted that hydrogen was trapped in these permanently shadowed regions. The impact transformed suspicion into direct evidence. Independent infrared observations from another lunar mission also detected the unmistakable signature of water ice exposed at the surface of several polar cold traps. The Moon was no longer simply a dry desert with a few unusual measurements. Hidden ice was real. Even then, it would have been easy to misunderstand why this discovery mattered. Water usually means drinking, survival, a future habitat for astronauts. That explanation is incomplete. Water becomes something entirely different once electricity passes through it. Split the molecule apart, and it produces hydrogen and oxygen. Together, they form one of the highest performance rocket propellants ever used. The same basic ingredients that once powered giant launch vehicles from Earth could, in principle, be produced far from Earth's gravity. Suddenly, the frozen soil inside those black craters stopped looking like stored drinking water. It began to resemble stored transportation. The importance of that change becomes obvious when gravity enters the story. Launching anything from Earth demands enormous energy. Every kilogram must fight its way out of the planet's deep gravity well. Rockets grow massive because most of what they carry is fuel needed simply to lift more fuel. The Moon plays by different rules. Escaping its gravity requires only a fraction of the energy needed to escape Earth's. If usable propellant could eventually be produced there, spacecraft would no longer need to haul every drop of fuel from the surface of our planet. They could refill much farther along the journey. The Moon stops being the destination. It becomes part of the road. That realization creates a new question. If lunar water changes everything, why not collect it anywhere on the Moon? Because the Moon is far less uniform than it appears. The South Pole contains an extraordinary combination found almost nowhere else. Deep crater floors remain in permanent darkness, cold enough to preserve ice for immense spans of time. Just above them, sharp ridges receive sunlight for most of the lunar year. Engineers see two neighboring environments serving opposite purposes. Sunlit peaks can generate electrical power. Nearby shadowed craters preserve frozen resources. Power and raw material exist almost side by side. Most other places cannot offer both at once. One crater gradually came to symbolize that hidden geography. Shackleton. At first glance, it is only another impact scar. Seen through orbital mapping, its meaning changes completely. Its rim receives extended periods of sunlight. Its interior descends into temperatures so low that trapped water molecules can remain frozen for billions of years. The crater transforms from a geological feature into strategic terrain. The map itself begins telling a different story. Instead of spreading evenly across the moon, valuable locations shrink to only a handful of coordinates. Scarcity changes behavior. When national space programs began selecting future landing regions, an unexpected pattern emerged. Different plans, developed independently, repeatedly clustered around the same south polar landscape. The reasons varied in detail, but the geography remained remarkably consistent. Access to permanent sunlight, access to permanently shadowed regions, access to the possibility of local resources. The convergence was not driven simply by symbolism. Flags do not require frozen craters. Infrastructure does. That shift quietly rewrote the meaning of returning to the moon. During the Apollo era, reaching the lunar surface was the achievement. The landing itself represented success. Today's planning increasingly treats the landing as only the beginning of something larger. Hardware is designed with the possibility that future missions could someday obtain essential materials locally rather than importing everything from Earth. Important uncertainties remain. Scientists still do not know exactly how the ice is distributed beneath the surface. It may exist as tiny grains mixed with lunar dust, thin frost coatings, or deeper deposits that have never been drilled directly. Extracting it in temperatures colder than almost anywhere else in the solar system remains an engineering challenge that has not yet been demonstrated on an industrial scale. No one is mining lunar water today. No one is filling spacecraft with lunar fuel. Those unknowns, however, have not prevented the strategic map from changing. The evidence already available was enough to overturn an older assumption. The moon is not simply a barren world waiting to be visited. It contains locations whose value comes from what they could enable beyond themselves. Return once more to the South Pole. The same black craters that once seemed like empty scars now represent frozen reservoirs preserved across immense stretches of time. The same narrow ridges that once looked like ordinary high ground now represent potential sources of continuous power. Together, they create one interconnected system that only became visible after the discovery of hidden ice. Nothing about the moon's landscape changed. The craters remained dark. The ice remained buried. Only the meaning of that landscape changed. What once appeared to be the end of humanity's journey into space increasingly resembles the first supply station on the road beyond it.